All right, everyone, here's another video covering chapter 8.4 of our textbook. If you are watching this, then I am going to assume that you have watched 8.5, worked really hard with the questions, and built a level of confidence and ready to take on something new. Yeah, before I forget, again, you may want to take out a paper and pencil because as opposed to you just copying simple notes, I'm going to work out a formula and do some example questions with you here. That is going to be your homework. Before I forget, or in case I have to clear the screen, please make sure you do it. We are going to do number 10 together in this video. I invite you to try it again after you do it together to get a better sense of what this formula and what surface area is all about. And without further ado, let's do it. This particular video is going to first cover, I'm going to give you the formula straight up. Okay, and you will find that it's a funky looking formula. For those of you who are interested, you are going to continue watching because I will try my best to give a reasonable explanation of where the formula comes from. For those of you who are not interested and simply want to see it in action, you can use a timestamp in the description section below and just jump to the examples. But I do invite you to take a look at that because it requires a little bit of deductive reasoning, some numerical, so some number literacy, and some logic. Okay, so even if you're not interested, at least just watch it and see it sort of, strikes a chord in you. Okay, strictly speaking, surface area formula: the surface area of a cone is pi r s plus pi r squared. Yeah, you're already scratching your heads and you're probably already thinking, I'm going to skip the explanation. Bear with me, okay? The surface area, you can also say this is pi r s times pi r r. The only difference between these two terms is the s versus the r. So why is it very similar and why is it also different? Before I answer that question, I must clarify what S and R stands for. If this is your typical cone, you are to calculate the surface area by calculating the area of the base, a flat base, which is obviously a circle, being a cone. And what is the area of a circle? That's going to be pi r squared. That's where this portion comes from. Which means this portion must come from the surface, right? It must come from this surface, outer surface. If this was an ice cream cone, it would be the part that you're actually holding. What is the area of that slanted surface? Okay, and let me actually write that down. Slanted right? And that's what the pi rs is, okay? So I'm going to try to explain to you why that makes sense. Before I forget, by r, I'm talking about the radius of the largest circular area of the cone, and by s, it actually represents the, well, if you've watched a previous video, I'm going to say this is basically the 2D hypotenuse. The slant length of this cone is the S of that formula. So why does that make sense? Well, first, and so this is the explanation portion. If you want to skip it, just go to the example and the timestamp. Here's my explanation, but it first requires a little bit of imagery. Imagine you have a circular piece of paper and you took scissors to it and you cut out a quarter, okay? And not only that, you took this side and you've brought it together so that they're sort of touching, and then you taped it up. What would that look like? Well, it's going to look like a little popped up cone. Because you see, if this circle was a full piece of paper, it would be a 2D object and it would be flat on the ground. But if this surface and the other surface that you cut off were to touch each other, that centerpiece will have to pop up. There's really no choice. If you don't believe me, cut out a piece of paper, okay? Cut out a piece of paper and cut out a circle. And then from that circle, cut out any piece that you want, right? Any little pie shape that you, or any little, I guess, pie slice that you want, and see what happens when you try to bring those papers together. It will end up popping up. Anyways, why do I bring this up? Well, I need to, number one, make sure you see the 3D aspect of it, the fact that it does pop up. And number two, you see these edges that you actually cut out? So this one and this one, or even if I cut out a larger slice, this one and that one, these edges essentially is the radius of the circle. And if I bring these two pieces together, seeing as that's a larger slice, my cone is going to be quite high compared to the previous cone. But where does this gray edge show up? Where is that gray edge when we turn it into a cone? Again, I invite you to try it. This radius of the flat circle ends up becoming the slant length of a cone. Think about it. Imagine it, or try it. This, I guess, hypotenuse length, for lack of a better term, is what we would call the slant length. Okay. Normally it would be R, but because when we turn it into a cone, it ends up being the slant. We won't call this an R, we're going to call this an S. So the radius of the portion of the circle that's going to turn into a cone, we're going to use the letter S. All right? Questions so far? That was a habit. You can't ask a question because you're watching a video. Wow. Moving on. Now that you have a better understanding of the 3D aspect of it, I'm going to appeal to your numerical logic by first clearing the screen in 3, 2, 1. Consider this. The area of a circle, okay, versus area of a cone. The ratio of an area of a circle versus the area of the circle that is to be a cone is very interesting when compared to the ratio created by the circumference. Okay, so if you're copying this down with me, very quickly, draw a little Pac-Man on both sides and draw a circle on another. Okay? Pause the video, and you can do that. For everyone else, let's keep going. The area of this circle, you know the formula is pi r squared. That is going to cover the entire 100% of this circular space. And for better visualization, how about I color that a nice pink color. I know I'm going to miss a spot. So for those of you who are sort of semi-cringy about me missing, like erasing a piece of, missing a piece of chalk on the whiteboard or the blackboard, please forgive me, okay? If I were to cut out 25% of this circle, how much of this cone is left? Well, I'm hoping you're guessing is 75%. So if I were to say the ratio between the area that could be covered by a circle versus the area that could be covered by a cone, it would be 75 to 100, or 3 over 4. Yeah? All right, so how about I turn that into blue because we're talking about a cone here. All right. In the same way, if we're talking about a circumference, in other words, the rim around it, if that was you and you were going to walk all the way around the circle, right? That would be the full 100% distance that could be traveled around the circle, and that would be pi r, 2 pi r, right? What about the distance after you cut out 25%? Compared to the full circle, how much of this can you actually walk around? How much of the original circumference are you traveling if you stop right there? I'm hoping you said 75%. Because just like the area, 1/4 of the distance you could have traveled was cut out. So what is the ratio? It would be, again, 75%, 75 over 100, or 3 over 4. The ratio between the area of a circle and a cone and the circumference of a circle and a cone are the same. And if ratios are the same, in other words, if fractions are the same, we could do some interesting cross multiplying and interesting algebra with it. Right? And so here is where it gets a little bit funky. I'm going to clear the screen again in 3, 2, 1. Here's where the proof is. I'm going to create a ratio between the area of the slant surface of the cone to the area of the base. And I'm going to compare it to the circumference that could be walked if the slant surface was a circle, was flattened out, versus the circumference of the actual circle itself. It's better if I write it down. So a slant surface area to the area of circle is going to be versus when it could have been a circle, is going to be equal to the circumference of the cone divided by the circumference of if it was a circle. Okay, let's get to it. A slant surface area, that's what we're actually looking for. If you remember, we're trying to figure out why the heck that portion of the formula, surface area is equal to this plus pi r squared, why this portion is called pi rs. So let's pretend the slant surface area is something that we do not know. But the area of the area that slant surface could have been would have, again, would be pi r squared. But remember, the radius of that lateral, the slant surface is represented by s. That's going to be pi s squared. Now, the circumference of the cone itself, so this little rim portion, that would be pi, 2 pi r, divided by, what is the circumference of that circle? If it was a circle, it would be 2 pi s. Whoa. If this is the number that we are looking for, then we can say with effectiveness, 2 divided by 2 is just 1, 1. Pi divided by pi is just 1, 1. And if I want to get the left side all alone, in other words, if I want to get rid of a division of pi s squared, I'm going to multiply both sides by pi s squared. I will get the surface, slant surface area is equal to r over s times pi s squared, or r s pi S, S. And S divided by itself is going to be 1, 1. So the surface area of the slant surface is R pi S, or in other words, pi R squared. So if the slant surface using mathematical ratios is pi RS, and the base circular area is pi R squared, then the entire surface area of the cone is going to be pi RS added with the pi R squared. It's a bit of a stretch. This formula can be proven using grade 12 math, basically calculus and integrals and beyond. But for our level in grade 9, that's the explanation. It's a bit long-winded. Hope you're still with me. I'm going to clear the screen. We're going to try page 447 or 448, number 10, together as an exercise. The remaining, 10 questions that I assigned, I'd like you to practice on your own time. So clear the screen in 3, 2, 1. Okay, so this is page 448, number 10. The frustum of a cone is the part that remains after the top portion has been removed. So think about a cone, and one day they decide to chop this top part off. So I'm going to redraw this cone. There it is, and it's going to look something like that. Okay, so that part has been chopped off. And please note that this circle is perfectly flat and parallel to the base, parallel to the floor, so you don't have to worry about any slants or angles. Calculate the surface area of the frustum to the nearest square meter. A couple of pieces of information that they give you. The height of the chopped off portion of the cone is 2 meters. The radius at the chopped off portion is 1 meter. The remaining height of the cone is 6 meters, and the base of this cone is 4 meters. Surface area of a regular cone, this is not a normal cone, of a regular cone is pi r s plus pi r squared. Pause the video and take a second to think of how you might approach this question. If my image sucks, well, go to the textbook that my Nelson has graciously provided and take a look at the image they provide there. Pause the video. Going once, going twice. All right, first things first. Here's what I'm going to do. Normally, what you can do is, which is what I'm going to do, I'm going to calculate the surface area of this of this cone as a whole. All right, but notice how this portion of the surface does not count. So I'm going to have to calculate the surface area of that cone portion and then subtract it from the whole. But what else? In cutting that, guess what surface I exposed? Now there's this top portion. Remember, this cone isn't going to be hollow. There's that top portion. And now I have to add the exposed top surface. There's a lot to be done, all right? So I'm going to see to calculating one large number, another number, and then another number to add and subtract all together. So as you can see, in this question, it's not enough just another formula. There's a whole bunch of stuff going on. Let's try to break it down into pieces. Let's see. Surface area of the whole uncut cone. And that is going to be pi rs plus pi r squared. What is r? It is given to us as 4 centimeters. What is S? Ooh, that I can only calculate if I were to use Pythagorean theorem. I need to find the S. So, if this was the slant of a full cone, the base would be a 4, and that height would be 2 plus a 6. In other words, it's 8. S squared is equal to 8 squared plus 4 squared, which is 64 plus 16. That is an 80. That means S is going to be square root of 80. The answer would be plus or minus 8.94. But again, the negative 8.94 is an extraneous answer, an extra answer that doesn't make sense in geometry. And so we have 8.94 meters. So let's do it. That means pi times r times s plus pi times r squared. Give me a second. Pi times 4 times 8.94 plus pi times 4 squared. That brings us to a surface area of 162.61 meters squared. Just for simplicity, I'm just going to do 163 meters squared. Now, let's calculate the surface of that top section. The top section of the cone, I am actually not interested in the circle portion. I only need the area of the surface, the slant surface, which means I only need the pi rs portion. This is why my explanation comes really handy, because you know that all we need is pi rs. I do not care about the pi r squared portion. So what is pi rs of that tiny, tiny cone? R is given to us. It's 1 meter. Take a look at the image. It is right here. But what's that slant? If you said 2 meters, it would be incorrect. This tiny cone has a height of 2 and a radius of 1. You could think about that as a 90-degree triangle with a height of 2 and a base of 1. What is the slant? It's the hypotenuse. I'll call that S. S squared is equal to 2 squared plus 1 squared, which is 5. S is going to be square root of 5, which is plus or minus, or in this case, just plus 2.236, 2.2. Therefore, pi rs is equal to pi rs. Pi times 2.2. That is 6.9115. Let's round it to 6.9 meters squared. The last bit, I need to calculate the area of that surface portion right here that has been exposed when I chopped off that little tip portion. So for this circle, the area of a circle, that's nice. We don't have to worry too much. It's just pi r squared. The radius of that cut out portion, the image already gave it to us as 1. Therefore, the area is going to be pi times 1 squared, which is just pi, which is 3.14 meters squared. So let's backtrack. The surface area of that entire cone, base and all, is 163. But I need to subtract the surface area of that top portion. And that was calculated to be 6.9. But after I cut it off, I exposed a new surface. Instead of the actual cone tip, I have with me a flat circle. And so, of course, because it's a new surface that I exposed, I have to add the area of that new surface. So 163 subtracted by the 6.9 added by the 3.14 is going to be 159.24 meters squared. The question asks for the nearest square meter, so it's going to be approximately 159 meters. Again, this is question 10. It's one of the harder questions, I'm sure, because it is closer to the end. It is right just before the chapter problem. Try the first number of questions, so numbers 1 to even 8, 1 to 9. And then when you feel a little bit more confident, try number 10 again. You could always use this video as an answer solution reference. And of course, the chapter question is open for you to try. In case you forgot or you don't want to go back to the initial part of the video, numbers 1 to 11 is your task. Get ready for another problem set soon. We are approaching the end of chapter 8, as you might imagine. And so you can expect something to be handed in soon. I hope that doesn't depress you too much and that you're still keeping up with your work. Please do this to the best of your ability. I know it's hard. Self-discipline yourself. Think of it as a once-in-a-lifetime challenge. Ask me questions through email, and I will always be available to help and answer. Best of luck, be safe, and hope to see you soon.